Okay, welcome to the Geometry Model Theory seminar. This week's speaker is María Martín Vega from Valladolid. She's going to tell us about Dulac's problem in free space.
Thanks, Patrick, for introducing me, and thanks also the other organizers, Tamara and Kyle. Well, I'm going to speak about a problem in my PhD thesis. And yeah, but I am doing currently the PhD with Fernando Sant and Nuria Corral. Okay, well, I will start doing a short introduction, then I'll explain the objective, and finally I will do the proof of the main theorem. Just to fix some notation, we work with analytic vector fields, with real analytic vector fields defined in analytic manifolds, and we will also work with formal vector fields. What we are interested in studying are the periodic solutions, the periodic trajectories of the vector field that are called the cycles, and especially the limit cycles that are those cycles that are isolated from others. Well, the Dulac's problem is a part of Hilbert's 16 problem. And it says that for a polynomial vector field in dimension 2, we have a finite number of limit cycles, and this number is uniformly bounded by some function of the degree. And the first part of this problem has been proved by Dulac's problem, that it says that for analytic vector fields, there are only a finite number of limit cycles around the singularity. Just some history in this problem, it was introduced by Dulac, and he gave a positive answer, but the solution wasn't accurate. So finally, Elias and Konekow in the end of last century proved this independently. So as a consequence, we have that for analytic vector fields in dimension 2, we either have a center configuration or we have just a finite number of cycles. One tool that we will use in this work is the Poincaré first-order map. If we take some cycle and a hyperplane that is transverse to this cycle, we can define the Poincaré map analytically in case this cycle doesn't contain any singularity, and is defined for some point. The image is just the intersection of the trajectory that is defined by the vector field, again with this hyperplane. In dimension 2, we have a bijection between the fixed points and the cycles that are intersecting this hyperplane. But in any other case, the cycles are defining periodic points that are fixed points for some iteration of composition of this Poincaré map. Well, to put some examples, in R2, as I said before, we only have two possible configurations whenever a Poincaré type map is defined. We can have a center, which means that the set of fixed points is just all the hyperplane of the Poincaré map, that is the identity. And a simple example that we have seen in many of the courses this semester is just this linear vector field that we can call it a linear non-degenerated center. In any other case, we have a focus configuration, which means that taking a sufficiently small neighborhood of the singularity, we see that the Poincaré map doesn't contain any fixed point. And well, it's a classic problem that distinguishing between these two possible configurations is called the center focus problem. And this is a very transcendental problem in the sense that it's not solvable just observing a finite k-yet of the vector field. To put also an example in R3, we can consider the previous example that it was just a linear vector field, add something in the vertical direction, and then we can study the distribution of cycles. In this case, it's easy because we only have a linear vector field, and we can find two possible behaviors. If C is different from 0, in this case, we only find a surface that is composed by cycles. But if C is equal to 0, we have a line of singularities, and all the spaces except this line, that is just the z-axis, is filled with cycles. So the question is, how are the cycles distributed for perturbations of this kind of vector fields? Well, we define these perturbations. What is important here, these are defined just in some coordinates. We can write them in this way. And what is important is that the linear part is never null because we don't let it be 0. And these functions are just analytic functions of order equal or greater to 2. And C can be 0. And well, we can notice that these vector fields are just perturbations of order greater than 2 of the ones I presented before. Here in R3, we don't have a topological classification of the orbits, so we have a difficult center focus problem. The tool that we will use is, I call it the local set of cycles, and they are defined in neighborhoods of a singularity that is placed at 0. This set is defined as the union of all the cycles that are completely contained in the set in the neighborhood U. And what I remark here is that these sets are not behaving like germs. And to explain this, I better show an example. Well, in this case, we have just a neighborhood and the set of cycles containing that neighborhood. But if we take a smaller neighborhood here, we see that, for example, this point is in the intersection of the set Cu and U prime, but is not contained in the set Cu prime because the whole trajectory is not included in the set U prime. So the property that we want to prove is Dulac's property. If we have an analytic vector field, we say that it fulfills Dulac's property if we have one of these possible situations. First, in some neighborhood, we don't find any cycle, that is the set of cycles is the empty set. And secondly, if we find some neighborhood of the singularity, where we find a finite number of surfaces, and these surfaces only intersect in the singularity, and the set of cycles is just the union of all of these surfaces, well, the closure of the set of cycles. So the objective of the talk is to prove this theorem. We have a perturbation of a linear non-degenerated center with the additional condition that the singularity is isolated, then we find that the vector field fulfills Dulac's property. And this is related to the original Dulac's problem because a consequence of this theorem is that the number of limit cycles that we find around the singularity is finite. So now we prove the theorem. First, we suppose that C is different from 0. This is an easier case because the singularity is semi-hyperbolic. Like C is an eigenvalue for this vector field. Then we can apply theory of invariant manifolds and find an analytic one-dimensional stable manifold or unstable, depending on the sign of C. And secondly, for every natural number, we can find a center manifold that is an invariant surface of class CR that is defined in some open neighborhood of the singularity. Another consequence of the center manifold theorem is that this manifold here contains all the trajectories that are globally contained in VR. That is that we can define them for every R time in R. And as a consequence, we find that all the cycles in this set are contained in the center manifold. To proceed with this proof, first we will blow up the stable manifold. This means that we do a blowing up whose center is the stable manifold, and we are substituting the center manifold by this kind of cylinder. And what we find here is that the inverse image of zero is defining a periodic orbit, a cycle, inside the divisor, and it doesn't contain any singularity. In fact, this cycle is containing the intersection of the center manifold with the divisor, or any of the center manifolds that we can define. So for the rest of the proof, we fix some center manifold, we fix the neighborhood where this center manifold is defined, and some plane that is transverse to both the center manifold and the cycle contained in the divisor. In this case, this cycle is free of singularities, the Poincaré map is analytic, and therefore the set of fixed points is also analytic. On the other hand, we have that all the cycles are contained in the center manifold. So the set of fixed points in particular is contained in the intersection curve of the center manifold with this hyperplane where the Poincaré map is defined. As the dimension is 2, we find a bijection between the set of fixed points and the cycles that are crossing this hyperplane. Now we have two cases. First, if we have a finite number of cycles around the singularity, we trivially have Dulac's property. Consider a neighborhood here small enough such is not containing any of these cycles. But if we have an infinite family accumulating to the singularity, that means that the singularity is in the closure of this family. These cycles are defining an infinite family of points, of fixed points of the Poincaré map. As this is analytic and it contains an infinite family, this means that the set of fixed points is just the whole curve where this set is contained. And using again the bijection of fixed points and cycles, we find that the whole surface is full of cycles. And in particular, we find that Dulac property is true in the second assertion of Dulac's property with just one surface, that is the center manifold. Here we find some consequences. First, just for the first case, we find that as the results are true for any of the choices of the center manifold, we find uniqueness of the center manifold. And in particular, as is defined by the flow of the vector field, this center manifold is locally analytic, and we can prove it for any point out of 0. So the final conclusion for this first case is that a vector field with that is a perturbation of a non-degenerated center fulfills Dulac's property in the semi-hyperbolic case. Now we study the case where C is equal to 0. This is completely non-hyperbolic case. And what we only have first is that we can write the vector field in this way. I want to remark that in the derivative of Z, there is some term that is that just depends on Z. That is not divided by any function of x and y, and this is because the singularity is isolated. We can also take b equal to 1 because otherwise you can multiply by some constant. As we have that the linear part doesn't define any eigenvalue, real eigenvalue, but it defines some imaginary eigenvalue that is not null. Tangent normal form applies here, and we can find some formal coordinates for some formal diffeomorphism such that the transform vector field is written in this way. Well, here you can see that this vector field is representing a radial vector field in the plane. This is a tangent vector field to the circles in the plane, and this is just the vertical vector. Tangent normal form can also apply to obtain an analytic normal form. because we are only working with a finite jet, and thus the diffeomorphism that we will use is just a polynomial diffeomorphism. So studying this vector field in the analytic normal form is equivalent to study the original vector field. And what is special here is that the L-jet coincides with the L-jet of this formal normal form. Well, the strategy of the proof is first studying the problem using the formal normal form. That is, yeah.
So you mean that for every L there exists an analytic vector CL subtract? The last sentence. Or is it an analytic?
Yeah, the analytic vector field such that this LJ is.
It depends on L. Or is it the same analytic vector?
Yeah, it's diffeomorphic. They are diffeomorphic. Yeah, I don't know. We use the formal normal vector field as a guide, and later we prove that these arguments that we are finding are valid in the analytic case. Just a diagram to understand it better. This is our original space. We have the formal diffeomorphism and formal coordinates, and we also have analytics diffeomorphism for every L, such that we find the normal form, the analytic normal forms. And with this diffeomorphism, we define the transform vector fields, and we will study these vector fields. Well, first we blow up the singularity. We do a real blowing up. This means that the blown up space has a boundary, and the boundary is the divisor, which is diffeomorphic to a sphere. This divisor is representing the direction of all the half lines that cross the origin. In this first chart, we have all the divisor is covering all the divisor except 2 points that are the north and south pole of the sphere. And secondly, we use the charts C2 and C3 to study the points that are not being covered by this first chart. We can take the total transform in the first chart. We will be from now on working with this first chart, and this is just the expression after this blowing up. What is remarkable here is that the derivative of theta is a unit. Well, here we can pick this as a 1. And the equation of the divisor, that is rho equal to 0, rho is dividing both the derivative of rho and the derivative of z. So as we had the derivative of theta is a unit, we can define a 2-dimensional vector field. In the formal case, this is autonomous because we don't have the angular dependence. And here these functions are series in rho with coefficients that are polynomials in Z. And just to remark that in this case, the coordinates theta is acting as a time. For L lower than infinity, we can define a non-autonomous 2-dimensional system that is an analytic vector field that has dependence also on the time here, that is just the angle theta. This series here are convergent series in the coordinate row, and with polynomial coefficients in Z, cosines of theta and sines of theta. And in fact, the LJ of both are the same. So now our first small result here is considering L to be large enough, larger than N, and just was the common factor of rho in both functions. The sets of singularities are the same. And in addition, they only have dependent set and have a finite number of connected components. This is an immediate consequence of the fact that this series have the same element. And as L is larger than n, we have that the angular dependence is multiplied by some power of rho. So in rho equal to 0, we find that there is no angular dependence. And thus these functions are just polynomials because in both cases they are polynomials in set. Well, now we will define some boxes. We will assume that the blowing up is non-decritical. And the critical case I will do a remark later, but it's a similar study. Considering the coordinates of the singularities of the two-dimensional system, we can take constant m to be as large as we want, constant epsilon as small as we want, and there is some constants delta, such that these boxes here, that I draw them better here, are boxes where the formal vector field is either set increasing or set decreasing. So after some computations, we can define, we find this lemma, and the sets that are just the boxes that we saw before, times the angular dependence, define flow boxes of the analytic vector field for L large enough. And this is a consequence of rho being always greater than 0, that is not reversing the trajectories. And we find that in these boxes, set is increasing or decreasing, and the trajectories behave something like this inside the box. They are twisting the divisor, and set is always increasing or decreasing, that is monotonic inside. And other particular thing is that it has two faces, an upper and lower face, and in one of these, the vector field is pointing inwards the flow box, and in the other is pointing outwards the flow box. So now we find this result, supposing that we have a neighborhood of the divisor whose height is lower than the height of any of the flow boxes. Then we find that, well, considering the projected space of this U tilde, we find that the set of cycles is not intersecting any of the flow boxes. To prove this, we suppose that there is a point that is contained in the set of cycles and is also contained in some of the flow boxes, in one of the flow boxes. So we define the trajectory, and as it's contained in the set of cycles, it should be a cycle. But we also have that the trajectory is living in some of the through one of the faces of the flow box. And as delta is lower than the minimum of all these heights, we find that the neighborhood minus the flow box, it has two connected components. And as this is a flow box, the trajectories cannot enter back to the flow box in the same phase. And we find a contradiction because the orbit cannot be a cycle and enter into the flow box since disconnected component. As a corollary for this result, we find that the set where the accumulation of orbits is possible in the divisor is the union of these orbits here that we can call characteristic orbits, and also the north and south pole that we haven't studied yet, so for the moment we include them here. And we can also prove this result for the critical case, but in the critical case, we can find that the flow boxes are pointing to the divisor. Now we have the vector field that I defined before, that is a formal vector field, and it admits resolution of singularities. But this vector field can have lines of singularities because it doesn't need to be reduced. So the resolution of singularities here is adaptive. First, we resolve both the singularities of the course of singularities, and we also solve the singularities of the reduced vector field. So after a finite number of blowing ups, because we are in dimension 2 and we have a theorem of resolution of singularities, we find that the vector field has a finite number of simple singularities, well, the transform vector field by these blowing ups. The charts that we are going to use in this part are these three. They are real blowing ups, and in all of them we do a translation of the origin to the singularity that we are treating, and we have a central chart that is covering all the new divisor except of the two corners, and an upper and lower chart that cover the two corners of the new divisor. And just I want to remark that these blowing ups are for the two-dimensional vector field, but are equivalent to do in 3 dimensions blowing ups along the cycles of the characteristic orbit. Well, after this composition of blowing ups, this is an example of a final situation. We can see that, well, in different colors I represented the different components of the divisor that we obtain with these blowing ups. And we have singularities that are corners and other singularities that can appear in the intermediate divisors. These singularities are all simple, and this means that the linear part of the vector field is not nilpotent in these singularities. The eigenvalues of this transform vector field have not a ratio that is a rational positive number. So the 3 possible final situations are these. In the first case, if the singularity is isolated and is in a corner, we find that the two separatrices of the singularity are just the components of the divisor. In the second case, we can suppose that there is a line of singularities, and the singularity is just the intersection of the line of singularities with the divisor. And in the third case, we can find that there is an isolated singularity that is not in a corner and is a simple singularity of the reduced vector field. That is after dividing by the equation of the singularities. And well, we are in the formal case, and in this last part, we have that the singularity is crossed by a formal invariant separatrix, because it's a simple singularity and we have always two separatrices. Well, with this last scenario, we find some invariant curves for the two-dimensional vector field. The branches of singularities define invariant curves for the vector field because they are branches of singularities. Well, in principle, we are in the formal case, so they are formal curves. And on the other hand, the formal separatrices are also defining formal curves of this vector. Well, translating this to the 3-dimensional problem, and knowing that the Lie derivative of this vector field through the angular vector field is equal to 0, these revolution surfaces are just formal invariant surfaces for the 3-dimensional vector field, only in the formal case. Now we treat the analytic case. As we could see, the resolution of singularities only used a finite k yet. So taking L to be greater than this k, we can follow the same sequence of blowing ups, but in the 3-dimensional case, and find that the vector fields just in the divisor are exactly the same each one in the proper coordinates. And therefore they will have the same characteristic orbits, and we can study the accumulation of cycles. In the first case, we have that the vector field, that the singularity of the vector field is a corner, and the two separatrices are in the divisor. So if we find cycles, we find them in this divisor. In the second and third case, we consider again this formal diffeomorphism, as I saw at the beginning, and we find the transformed surface of the invariant surface of the formal vector field, and we find that these surfaces are invariant for the analytic vector field. In any other point, we cannot find any accumulation of cycles because the flow boxes argument is applying recursively after any of these blowing ups. So if we find accumulation of cycles in the divisor, it's only possible on the characteristic orbits that are corresponding to the cases 2 and 3. Now we study the Poincare map. We can define this Poincare map in a plane that is transversal to these characteristic cycles, and these characteristic cycles don't contain singularities, so they are defined analytically. Well, we also find that this curve, that is the intersection of the surface with this hyperplane, is an invariant curve for the Poincare map. So if, as a remark, if this surface was convergent, then this curve is also convergent. If it wasn't convergent, it's just a formal invariant curve. We will divide this proof in two cases. First, if gamma is a formal invariant curve that doesn't contain fixed points, or if it's just a curve of fixed points, and thus an analytic curve, so convergent. Well, suppose that we are in the first case, or curve gamma doesn't contain fixed points. So we have two possibilities. We find that if it can have an eigenvalue not equal to 1, because we are working with diffeomorphisms, or we can find that all the two eigenvalues are 1, P is tangent to the identity. In the case that we find another eigenvalue, as we know that the divisor is defining a curve of fixed points, the only periodic points will appear in the divisor, so we are done here. And in the second case, we're in the conditions to apply this theorem that is in an article of Lopez and Sant. We have that the Poincare map is tangent to identity, that we have a curve of fixed points that is not of fixed points, but is formally invariant. And thus there exists at least one parabolic curve that is attracting or repelling and is asymptotic to this invariant curve. Well, this is not giving the result that we want, but other techniques in this article that I won't explain, we find that there cannot be periodic points in cones sufficiently small to these parabolic curves. So if P doesn't have periodic points, the vector field does not have cycles intersecting the plane where this Poincare map is defined. So now we go to the other case, and we can suppose that gamma is a curve of fixed points. Then this curve is analytic, because this is an analytic diffeomorphism, and we can consider it as a graph. After a change of coordinates, we can translate this curve just to the curve set equal to 0. We can write the Poincare map in this difficult way. We have that the divisor and the curve of fixed points that is set equal to 0 are curves of fixed points, so the powers here are greater than 0. Secondly, just to treat the case that is more interesting, we can suppose that R1 and R2 are greater than 0. And the other functions are just analytic functions. One important property here is that if Z is greater than 0, the coordinate set of the image is also greater than 0. And this is because this Poincare map comes from a flow of a vector field with an invariant surface that is convergent and cannot be crossed by any orbit. Well, now we have I explained that we can restrict our Poincare map two cones because otherwise we can cross a flow box and we're in a region that is not interesting. So after blowing ups, we can restrict this cone, this end here, to be as large as we want. So considering some n that fulfills this property, we can see that this fraction here goes to 0 when rho is going to 0. Well, it's just for this part of the diffeomorphism. This implies when we are not in the line of fixed points, if rho n set n is the image of another point, then either this rho is lower than the image, or vice versa. This implies that rho is monotonic inside this small cone, and therefore we cannot find periodic points of the Poincare map. As we don't find periodic points of the Poincare map inside this cone, this implies that there cannot be cycles intersecting this cone. So the unique cycles are contained in the surface. Well, now we prove already that if we find cycles are in surfaces that are intersecting the characteristic orbits that we have found. But still, we need to study the north and south poles of the initial divisor, and we do it using an iteration of blowing ups. They look like something similar to this. If you recall, the chart C2 is similar to the chart C2 that we had before, and the chart C1 is similar to the chart C1 that we have been using all the time. So after an iteration of blowing ups, we find this condition here, that is that the derivative of z is just some power of z times a unit. So this z is a monotonic function around the origin of the last chart after the iteration. And we achieve this situation because of the condition that I saw in the beginning of this part, that the singularity is isolated. Well, taking L to be large enough, as we have similar LZ, we find also this same situation. And what we find is this lemma that after enough number of set direction blowing ups, there is a small neighborhood of the origin of the last chart, where the set of cycles is not intersecting this neighborhood V, because the function is monotonic, and we cannot define any monotonic function along in an orbit. Sorry. So what we need to study is the intermediate charts, but the intermediate points of these charts are studied similarly to the chart C1 that we did at the beginning. So in the final situation, the first chart is given a finite number of characteristic orbits, and only inside of them we can find surfaces that are composed by cycles. After several blowing ups of the origin C2 and C3, we find that in these intermediate components, we find also a finite number of surfaces that are filled with cycles and are tangent to the axis Z, but this contact of tangency is of finite order. And in the end, the conclusion is that perturbations of linear non-degenerated center are fulfilling Dulac's property. Well, I think I've been too fast, but that's all.
Very much.